Thunderstorms, wind shear, and microbursts can all present serious threats to your flight operations. This program helps you understand the incredible forces behind these phenomena. It also points out warning signs that will help you avoid the associated weather hazards. It begins by showing you the inner workings of a thunderstorm, continues by explaining the varied sources of wind shear, and wraps up with a demonstration of the tremendous destructive power of microbursts. From a great distance, thunderstorms are a thing of curious beauty. But up close, they can represent a serious hazard to flight. According to the National Oceanic and Atmospheric Administration, 16 million thunderstorms occur throughout the world each year. This means that at any one time, there are over 1,800 thunderstorms in progress. And these storms produce over 100 lightning strikes per second. In the United States, the highest frequency of thunderstorms is in the southeastern region, but many tremendously destructive storms take place in the Midwest and eastern states. The Rocky Mountain region is also a good producer of these storms. As you recall, there are three conditions needed for the formation of a thunderstorm. They are a relatively high moisture content, air that tends to be unstable, and some form of lifting action. Moisture in the atmosphere is primarily the result of evaporation of liquid water into water vapor. The main source of moisture is large bodies of water, but the soil and plants, small lakes, and streams are other sources. Once water is in its gaseous state, the winds can transport it many thousands of miles before the process of cloud formation takes place. Stability is the atmosphere's resistance to vertical movement. Stable air tends to inhibit cloud formation, precipitation, and severe weather. Unstable air, on the other hand, allows the vertical air movement necessary for the formation of towering cumulus clouds. This type of air can lead to significant cloud development, turbulence, and hazardous weather. But some sort of lifting action must provide the initial boost to start the unstable air on its upward travel. This lifting can result from various sources, such as rising terrain, converging airflow, fronts, or convection from heating of the Earth's surface. Isolated air mass thunderstorms generally form in warm, moist areas where the lifting force is provided by convection. This type of thunderstorm is most common during hot summer afternoons. As the sun warms the ground, some of the heat is transferred to the boundary layer of air next to the surface. If this air is warmer and therefore less dense than the surrounding air, it begins to rise. An air mass thunderstorm can also be triggered by orographic lifting. Here, sloping terrain forces the air upward as the air mass flows up the windward side of the mountain. Thunderstorms associated with this type of lifting action are normally scattered along individual mountain peaks, but they could also cover large areas. Another triggering mechanism is converging airflow. For example, when the outflows of two thunderstorms converge, they can begin to rise. This, in turn, can form a third thunderstorm. Fronts can also provide lifting action when cooler, denser air from one air mass forces the warmer, unstable air of another air mass aloft. This often produces a line of thunderstorms which is difficult, if not impossible, to penetrate. When these frontal thunderstorms occur as a result of a warm front, they are often obscured by stratiform clouds. So be alert for thunderstorms whenever there is showery precipitation near a warm front. With a cold front, the cumulonimbus clouds are often visible in a continuous line parallel to the frontal boundary. But regardless of the lifting action, all thunderstorms develop in a similar manner. For the remainder of this discussion, Let's consider the thunderstorm which was initially lifted by surface heating or convective action. As the parcel is lifted, it expands due to the lower atmospheric pressure. This expansion causes a decrease in temperature due to a process called adiabatic cooling. The rate of temperature change with altitude is called the lapse rate. The adiabatic lapse rate varies depending on the moisture content of the air. For unsaturated air, the rate is about 5.4 degrees Fahrenheit or 3 degrees Celsius for every 1,000-foot change in altitude. The dew point also decreases with altitude, but at a rate of just 1 degree Fahrenheit per 1,000 feet. As a result, the temperature and dew point converge at about 4.4 degrees Fahrenheit for every 1,000-foot increase in altitude. You can use this information to find the approximate location of the cloud bases along your route of flight. Just find the surface temperature, subtract the dew point, divide by 4.4, and multiply by 1,000. For example, if the surface temperature is 82 and the dew point is 60, the cloud bases should be approximately 5,000 feet AGL. This altitude represents the condensation level where water vapor condenses on the particles, such as salt, dust, or combustion byproducts, which are always present in the air. As the air continues to rise, more water vapor condenses, causing the cloud droplets to grow larger. As condensation occurs, latent or stored heat is released, reducing the cooling rate of the rising air, which in turn makes it warmer and less dense than the surrounding air. This further increases the buoyancy of the air within the cloud. In contrast, evaporation removes heat from the air. This is why people feel cold when they get out of a swimming pool, even on a very warm day. During the convective process, condensation can transfer great quantities of heat energy to the cloud, causing it to become less dense than the atmosphere. The resulting severe updrafts can reach several thousand feet per minute. At this rate, a harmless-looking puffy cumulus cloud can quickly materialize into a hazardous cumulonimbus cloud. In its initial or cumulus stage, a thunderstorm cell is composed of strong updrafts. As the warm air rises in the updrafts, it's replaced by denser surrounding air that flows into the low-pressure area below the base of the cloud. The turbulence that results from this air movement can reach severe levels and is the major flight hazard associated with the cumulus stage. There may also be some icing within the cloud above the freezing level, and your aircraft could trigger some lightning. Remember, some of these clouds can develop faster than your aircraft can climb. If you try to climb over them, you might just find yourself inside a developing thunderstorm with strong updrafts and severe turbulence. During the cumulus stage, the strong updrafts keep any precipitation aloft. It's during the mature stage that the precipitation grows large enough to fall to Earth. Precipitation can develop in two ways. The Bergeron or cold cloud process, which occurs in the portion of the cloud above the freezing level, and the coalescence or warm cloud process, which is common in the warmer sections of the cloud below the freezing level. First, let's look at the section of the cloud above the freezing level. In this area, ice crystals and liquid water droplets coexist. Moisture which remains in liquid form at an altitude above the freezing level is referred to as being supercooled. These supercooled droplets are most common between 0 and minus 15 degrees Celsius, but have been observed at temperatures as cold as minus 40 degrees Celsius. This moisture will freeze rapidly should something, such as an aircraft, disturb it. Because different vapor pressures exist over water and ice, molecules can escape more readily from the liquid droplets than from the ice crystals. The water vapor is then deposited on the ice crystals. This process causes the ice crystals to grow and the supercooled liquid droplets to shrink. In time, the ice crystals become so large that the updrafts can no longer keep them aloft and they begin to fall, turning to rain as they descend through the freezing level. These raindrops continue to grow through the collision coalescence process, which is where larger raindrops collide with smaller drops and merge together. The raindrops also grow through wake capture coalescence. As water droplets fall, they create a wake. Within this area, the air resistance is less, so water droplets of similar size will overtake the leading drop and merge with it. However, aerodynamic drag and collisions with other large drops limit their maximum size to approximately 1/4 of an inch. At that time, they flatten out and break apart. The smaller sections then collide with other droplets to once again make larger drops. As the number of droplets increases, the intensity of the resulting precipitation also increases. As precipitation increases, visibility and airplane performance decrease. Recent studies have shown that in heavy precipitation, the rain buildup on an airfoil can result in a 30% loss of lift and as much as a 20% increase in drag. The falling precipitation also initiates downdrafts as it creates drag on the surrounding air. As the downdrafts become more intense, they draw in the cool, dry air around the cloud. The precipitation then evaporates into this dry air, further cooling the downdrafts and increasing their magnitude. Strong turbulence is present in the shear between the up and downdrafts and presents a very serious hazard to aircraft. Turbulence has been encountered several thousand feet above the cloud and up to 20 miles from the storm itself. As the downrushing air reaches the ground, it spreads outward, producing a sharp drop in temperature, a rise in pressure, strong gusty surface winds, turbulence, and wind shear. The leading edge of this outward flow is commonly referred to as a gust front. Wind shear, microbursts, and their associated hazards will be discussed later in this program. Hail also goes through a development process similar to rain, but with very different results. Hail, along with turbulence, represents some of the greatest hazards to aircraft. It begins as small ice pellets that grow as they collect supercooled water droplets. The hail can then rise and fall in the air currents inside the cloud until it is too heavy to be supported by the updrafts. At that time, it will fall to Earth. The size of hail varies widely, depending on the strength of the updrafts and the availability of supercooled water. But regardless of size, it presents a serious hazard. In fact, hail only a ½ inch in diameter can do substantial damage to an aircraft. You can encounter hail outside the thunderstorm, especially in and under the anvil. Therefore, if you're circumnavigating a thunderstorm, allow plenty of clearance and avoid the anvil area. Another serious hazard associated with thunderstorms is a tornado. Tornadoes are far more common in the United States than in any other country, with the greatest concentration in the central and southeastern areas. This activity peaks in the late spring and early summer, then drops off in the winter months. A tornado is actually a violent vortex of low-pressure air that extends down from a cumulonimbus cloud. Air near the ground rushes into this low-pressure vortex. As the funnel moves along the surface, it essentially vacuums up debris. At times, the funnel might not be visible. In this case, the only sign of potential tornado activity will be swirling debris on the surface. Winds within the vortex are believed to reach as high as 300 miles per hour. This tremendous power can destroy virtually everything in its path. Tornadoes can occur with isolated thunderstorms. Typically, though, they form in the storms that accompany fast-moving cold fronts. No program on thunderstorms would be complete without a discussion of lightning and thunder. As a towering cumulus develops, a large electrical charge separation builds up within the cloud. Lightning results when this electrical charge becomes strong enough to jump from the cloud to the ground, to another cloud, or to an opposite electrical charge within the same cloud. Although the process that creates lightning is not fully understood, it is enhanced substantially when the cloud grows above the freezing level. As the outer boundaries of water droplets start to freeze, positive ions, or particles with a positive electrical charge, flow to the area of ice formation. This creates an outer shell which is positively charged and a center which is negatively charged. When the interior freezes and expands, it shatters the outer shell. The droplet can also be broken up by colliding with other particles. In either case, the lighter pieces are then carried in the updrafts to the top of the cloud. The heavier, negatively charged particles fall to the bottom of the cloud. The cloud top now has a net positive charge, while the lower part has a net negative charge. While this process will eventually produce enough of a charge separation to cause lightning, it is believed that a second process also comes into play. This process is dependent on the first in that positive charges must already be deposited at the top of the cloud and negative charges in the lower portion. Because opposite charges attract, charges within large drops or ice crystals align themselves, so most of the negative charges are on the top and most of the positive charges are on the bottom. As smaller cloud droplets are being carried aloft in the updrafts, they collide with the bottom of the drops or ice crystals. The droplets then bleed off some of the positive charges and carry them to the top of the cloud. The larger drop or ice crystal is then left with a net negative charge. Because of its size, it eventually falls to the bottom of the cloud. As the negative charges build at the bottom of the cloud, they repel the negative charges on the Earth's surface. This leaves the area below the cloud with a positive charge. This positive charged area acts like a shadow that follows the cloud as it moves. When the cloud has a very intense negative charge at its base, it seeks to neutralize itself by discharging to a positive area. This discharge is what we see as lightning. When it discharges, it goes to the most accessible opposite charge. This is usually within the cloud itself or between clouds. However, the most spectacular observed lightning is from the cloud to the ground. The following discussion covers a lightning strike from the cloud to the ground, but the process is basically the same for any lightning discharge. Lightning begins when a negatively charged pilot leader descends from the cloud. This leader forms a conductive path approximately 8 inches in diameter and from 35 to 150 feet long. At this point, the electrons in the cloud begin to descend down the path. This recharges the path and causes additional leaders to extend earthward. These leaders are called step leaders because they seek the most conductive path to the ground and may try several branches before the best is located. As the path is extended, the electrons from the cloud extend further downward. The final step leader takes place a few feet above the Earth, where it is met by a rising positive flow from the surface. With the path completed, the positive ions on the Earth can now flow to the cloud and neutralize the lower portion. This upward flow is referred to as the return stroke, and because it energizes the air molecules and illuminates the path, we see it as lightning. Before the path dissipates, the first stroke is followed by additional strokes which further neutralize the negative charges in the cloud. What appears to be a single lightning flash can actually be 3 or 4 strokes. Even more important to remember is that this flash of lightning that has taken so long to describe actually takes less than a half second to occur, and that includes the leaders and 3 or 4 return strokes. The peak current in the channel can reach 10,000 amps, and the air in the channel can be heated to a temperature hotter than the surface of the sun. This causes the air on the path to expand violently, producing the sound waves we hear as thunder. But just what type of threat does lightning pose to you and your aircraft? Although most lightning strikes don't result in crashes, they can cause damage to the aircraft surface or its instruments and systems. This damage can include holes burned in the aircraft skin or propeller tips, movable parts like aileron hinges welded into place by the extreme heat, permanent magnetic compass errors, temporary interruption of the power supply from the alternator or generator, and momentary or total disruption of the avionics. Although it's unusual, lightning can even ignite fuel vapors in a nearly empty tank. Sometimes the shock wave of the thunder bends metal, breaks windows, or causes compressor stalls in turbine engines. Air crews can also be affected by lightning and thunder. Temporary blindness from the flash can last for 30 seconds or more, and the noise from the thunder can impair hearing. As you can see, the mature stage of a thunderstorm can contain very violent weather, which usually lasts about 30 minutes. However, as the storm moves, it can encounter fresh supplies of warm, moist air and regenerate itself with new cells as the old cells are dissipating. A storm is considered to be in the dissipating stage when downdrafts begin to dominate the air motions within the storm. This cuts off the supply of warm, moist air from the lower atmosphere. During this stage, strong upper-level winds at or near the tropopause tend to shear the thunderstorm tops, creating the familiar anvil formation on the downwind side. However, the anvil doesn't always signal that the thunderstorm is in the dissipating stage. It sometimes occurs in the mature stage and is accompanied by severe weather. Now let's look at some general rules for flight in the vicinity of a thunderstorm. These guidelines can be found in the Airman's Information Manual. The first and foremost is avoid thunderstorms if at all possible. This includes not taking off or landing if a thunderstorm is approaching. A sudden gust front producing low-level turbulence could cause a loss of control. When airborne, remain at least 20 miles away from any thunderstorm identified as severe or which has an intense radar echo. This is especially true on the downwind side of the thunderstorm and under the anvil of a large cumulonimbus. Remember, frequent lightning indicates a higher probability of a severe thunderstorm. You should also regard any thunderstorm with tops 35,000 feet or higher as being extremely hazardous. If a cloud mass contains embedded thunderstorms, don't fly into the clouds unless you have airborne radar. When the storms are scattered, circumnavigate them. You should also circumnavigate the entire area if the area has 6/10 thunderstorm coverage or more. don't try to go between the cells. And don't attempt to fly under a thunderstorm, even if you can see through to the other side. Turbulence, wind shear, and hail under the storm could be disastrous. If you try to fly over a thunderstorm, clear the clouds by at least 1,000 feet for each 10 knots of wind speed at the cloud top. For example, if the winds are 70 knots at the top of a 35,000-foot cloud, you should clear the tops by 7,000 feet, meaning you would have to be at 42,000 feet. And never trust the visual appearance of a cumulonimbus cloud to be a reliable indicator of the turbulence inside a thunderstorm. Avoiding a thunderstorm must be your top priority. But as a last resort, if you can't avoid flying through a thunderstorm, the AIM recommends a few things to do before you enter the cloud. First, tighten your seatbelt and shoulder harness and secure all loose items. If possible, plan a course which will take you through the thunderstorm area in the shortest amount of time. And to avoid the most severe icing, try to penetrate the thunderstorm area below the freezing level, or at an altitude well above the -15 degrees Celsius level. You should also verify that your pitot heat and engine anti-ice systems are on. In addition, establish the power settings for turbulence penetration airspeed recommended in your aircraft manual. To avoid temporary blindness from lightning, turn up the cabin lighting to its highest intensity. If you're using an autopilot, you should disengage the altitude and speed mode. If you don't, the autopilot could place unnecessary stress on the aircraft. And if using airborne radar, occasionally tilt the antenna up and down. This lets you detect convective activity at altitudes other than the one being flown. When penetrating the thunderstorm, the Airman's Information Manual recommends that you keep your eyes on the instruments. Looking outside the cabin only increases your chances of becoming blinded by lightning and inducing vertigo. And don't change power settings. Maintain the settings established for turbulence penetration. You should, however, try to maintain the attitude of the aircraft, but let the airplane ride the waves within the thunderstorm. Trying to maintain a constant altitude increases the stress on the aircraft. And finally, the AIM recommends that you don't turn back once you've decided you can't avoid a thunderstorm and have actually entered the storm. A straight course will most likely get you through the hazards quicker and safer than making a turn. Turning maneuvers also increase the stress on the aircraft. The best way to avoid a thunderstorm is to know that a potential for one exists. The best way to get this information is from a thorough weather briefing, whether you do it with a personal visit, through a computer briefing, or over the phone. Be sure to get as much information as you possibly can, including convective sigmets and convective outlooks. Then, when airborne, keep abreast of changing conditions by monitoring any available information, including en route flight advisory service. And remember that avoiding a thunderstorm is the best policy to ensure a safe trip. Now, let's turn our attention to wind shear and microbursts. Although these weather phenomena are commonly associated with thunderstorms, they are not exclusive to them. Recent weather research using the most sophisticated equipment available has shown that wind shear and microbursts are even more powerful and more common than first thought. Although most of the documented accidents and incidents involve air carrier aircraft, this doesn't diminish the significance to general aviation aircraft. Over 600 lives lost, 250 injured, and billions of dollars in property damage are statistics which drive home the point that every pilot needs to be thoroughly familiar with these hazards. Wind shear is a rapid change in wind speed and/or direction in a relatively short distance or time. It's most serious when the change occurs during the approach or departure phases of flight. But wind shear can occur at any altitude and can be in a horizontal or vertical direction or both. Severe turbulence is almost always associated with wind shear. You can encounter wind shear on a hot summer afternoon or on a cold winter's day. You can be VFR or IFR. It makes no difference. During this part of the program, we'll look at several types of low-level wind shear, including the most serious form, the microburst. Let's begin with a look at some general sources of low-level wind shear. Although our main emphasis is on the wind shear produced by convective weather, you should be aware of the other potential sources. Any obstruction to the normal prevailing airflow can produce wind shear. This includes passes through mountain ranges, hills with sharp drop-offs, buildings, and trees. Mountain waves and downslope winds are also common wind shear producers. Temperature inversions are another source of wind shear, especially when the warm air above the inversion layer is in motion. A front is often a catalyst for wind shear. A cold front, for example, can produce a sudden wind shift and an increasing headwind. In a warm front, the wind shear tends to be more pronounced in the vertical than it is in a cold front. Large changes in headwind and tailwind components can occur within 1,000 feet of the surface. The nocturnal inversion can cause the winds to increase above the inversion at 1,000 to 2,000 feet above the surface, while the low-altitude winds decrease. This causes strong wind shear and is especially prevalent in the central U.S. during spring and summer. Lake and sea breezes can produce flow patterns of cool and warm air that result in low-level shear. Although the types of wind shear we've just covered can be significant, the most serious forms are produced by convective weather. In fact, 65% of all wind shear accidents can be attributed to convective storms. It's important for you to realize that wind shear hazards normally associated with thunderstorms are not confined to major cells, but can occur near any strong convective cloud. Let's look at what happens when convection starts to develop. First, there is an inflow of warm air over a fairly broad area. This usually causes a wind shift toward the storm and an increase in wind speed. This is your wake-up call that wind shear is becoming a strong possibility. As you recall, when the convective storm enters the mature stage, a wide area of rain-cooled air begins to descend out of the cloud base. When this air reaches the surface, it forms a large dome of cool air that rushes out to form a gust front. A strong wind shear is created as the cool outflow forces the warm inflow up and over the gust front. The leading edge of the gust front can produce strong, gusty surface winds, an increase in pressure, a dramatic wind shift, and a temperature drop. The gusts from the outflow may exceed 50 knots and may extend many miles from the storm. In this view, we can see how the prevailing wind and movement of the storm influence the extent of the gust front. The front advances more rapidly in the direction of the storm's movement, and its advance is slowed on the upwind side. Let's look now at airplane performance as it relates to horizontal, low-level wind shear. An approach where a tailwind or calm wind switches to a headwind is a performance increasing phenomenon. and produces an increase in airspeed as the airplane penetrates the shear. This increases lift. As a result, the airplane tends to balloon above the glide path, increasing the chances of a long landing or an overshoot. On the other hand, a headwind that switches to a tailwind or calm condition is a performance-decreasing wind shear. An aircraft penetrating this shear will experience a decrease in airspeed and a corresponding loss in performance. The airplane descends below the glide path, which might lead to a landing short of the runway. During the takeoff phase of flight, the most serious situation is a performance-decreasing wind shear where a headwind or calm condition switches to a tailwind. The loss of airspeed, lift, and performance as the airplane enters the tailwind can exceed its ability to climb out of the wind shear and could cause the aircraft to stall. The best advice is to avoid approaches and departures during potential wind shear conditions. Due to the limited thrust-to-weight ratio in a general aviation airplane, a low-level wind shear encounter can be fatal. You should remember that wind shear can occur at any altitude. Although an encounter at altitude may not appear critical, it can produce severe turbulence and, in some situations, can exceed the performance capabilities of an aircraft. Let's turn our attention now to another source of wind shear. Beneath convective clouds lurks the most dangerous form of low-level wind shear, the microburst. In extreme cases, it can produce downdrafts in excess of 6,000 feet per minute and horizontal winds of 120 knots or more. This can occur in an area as small as 2 miles in diameter. The evolution of a microburst begins in the mid-levels of a convective cloud, normally between 10 and 20,000 feet AGL. As a cold pocket of moisture-laden air becomes too dense to stay aloft, it begins to fall. Remember that evaporation within the pocket enhances the cooling effect and further accelerates the downdraft. The diameter of the downdraft is typically less than 1 mile as it descends out of the clouds. When the microburst strikes the ground, it spreads out, usually in an asymmetrical pattern. An unusual characteristic is an acceleration of the outflow, rather than the typical deceleration due to surface friction. As the air rushes out, it curls to produce a ring of low pressure. This vortex ring enhances the wind shear by increasing the horizontal speed at the outer edge of the surface boundary layer. Vortex rings are often seen as swirls of dust or precipitation. In fact, multiple vortex rings may accompany a single microburst event. Usually only a portion of this ring is visible. The duration of a single microburst usually does not exceed 15 minutes, with the maximum winds normally increasing during the first 5 minutes. But under the right conditions, multiple events can occur over a wide area and for an extended time. As we mentioned before, microbursts are always associated with convective weather, although not necessarily with thunderstorms. There is some indication that perhaps 1 in 20 thunderstorms produces microbursts. Equally important, however, is the fact that microbursts can occur with relatively benign cumulus clouds that appear totally inactive. In fact, microbursts are classified according to the type of environment in which they occur, wet or dry. A wet microburst is normally associated with a heavy rain shaft. It may first appear as a darkened mass of rain descending through light rain. The vortex ring often can be seen as a well-defined, foot-shaped extension from the main rain shaft. Because of the relationship of the vortex ring to the prevailing winds, only a portion of the ring is usually visible. Low-level scud clouds may appear above the foot as the vortex ring curls and condenses. In contrast, a dry microburst is usually associated with high-altitude cumulus clouds that have bases up to 15,000 feet AGL. This type is extremely dangerous because the cloud can appear harmless, and the moisture may have totally evaporated by the time the microburst hits the surface. In this situation, the air is normally dry at the surface with more moist air aloft. In fact, a key factor for a dry microburst is that the temperature dew point spread at the surface is high, frequently 30 to 40 degrees Fahrenheit. As precipitation falls from this type of cloud, it evaporates, forming the characteristic virga. Evaporative cooling increases the relative density, which accelerates the descending air. In these dry microbursts, the vortex ring is often seen as blowing dust, debris, or flailing trees. Let's look now at what happens to an airplane that penetrates a microburst. As an airplane enters the microburst, it encounters an increasing headwind. This usually causes an increase in airspeed and altitude. This is followed by a severe downdraft, then a tailwind as the airplane exits the microburst. The resulting performance decrease can leave the aircraft with a dangerously slow airspeed and high descent rate close to the ground. An encounter with the edge of a microburst can cause a wide range of control problems. Sudden changes in the crosswind component may make runway alignment difficult. Wind speeds also may exceed the maximum crosswind component for the aircraft. If the edge of a vortex ring is encountered during an approach, it can produce rapid pitch, roll, and yaw variations, as well as severe turbulence. The established procedures for dealing with a microburst encounter are directed toward air carrier types of aircraft, with little published for general aviation aircraft. Again, the best course of action is to avoid situations where microbursts might exist. With this in mind, let's review the visual cues to help you avoid potentially dangerous situations. Anytime convective weather is present, be alert for microburst activity, especially in a shaft of rain beneath any convective cloud. A dark mass of moisture descending within a rain shaft is a good indication that a wet microburst is about to reach the surface, while a foot-shaped outflow from a shaft of rain is a positive indication that a microburst has reached the surface. You may also see scud clouds above the outflow. A warning sign for a dry microburst is the presence of virga underneath a cumulus or harmless-looking convective cloud. This is particularly true in the western U.S., where the air is dry. If it is accompanied by a partial ring of dust or flying debris, you can be sure it is a microburst. Also, watch for blowing dust or flailing trees in the departure or arrival path. At night, lightning may be your only cue of thunderstorm-related microburst activity, although microbursts may be present without lightning. Visual cues are not the only means of identifying microburst and low-level wind shear activity. One of the most important ways is through the use of pilot reports. A good wind shear PIREP should include a description of the condition, the loss or gain in airspeed, and the location and altitude where these conditions were encountered. Weather reports and forecasts are also excellent sources of information. Make sure you periodically review how to interpret these items. On surface aviation weather reports, watch for an indication of thunderstorms with rain showers, blowing dust, a large temperature dew point spread, and gusty surface winds. Also, look for cumulus, towering cumulus, thunderstorms, or virga. An unscheduled special observation, SP, or a scheduled record special observation, RS, should be looked at carefully for signs of changes in convective activity. Also, look for wind shear PIREPs in the remarks section of the report. Compare the winds aloft forecast at the first reporting level with the surface winds at the airport. If there's a large difference in speed and/or direction, you can anticipate wind shear during the approach or departure. In terminal and area forecasts, be alert for the development of thunderstorms, gusty winds, or convective weather. In addition, look for indications of low-level wind shear and frontal passage or associated weather changes. SIGMETs, AIRMETs, severe weather watches and alerts, and center weather advisories are excellent indications that wind shear and microburst activity may be present. To further help you when operating in areas where a wind shear or microburst might be present, some airports have installed low-level wind shear alert systems called LWAS. With these systems, instruments that sense wind direction and speed are strategically placed around the airport. Controllers use this information to issue wind shear alerts such as
wind shear alert, center field wind 270 at 10, south field boundary wind 140 at 30.
The latest version of LWAS issues much more specific alerts such as
wind shear alert, expected 20 knot loss, 2 mile final, threshold wind 260 at 10.
These alerts give you a good indication that wind shear is present and that extra care should be taken. But the earlier systems do have some limitations. Due to the spacing of the sensors, a microburst may go undetected, especially in the early stages of development. The latest version of LWAS, currently installed at Denver and New Orleans, has sensors that are spaced much closer than older systems and are capable of detecting a microburst and issuing an alert.
Microburst alert, expect a 40 knot loss, 1 mile departure.
Always avoid a situation like this. And remember, the detection equipment is on the ground, not in the air. So it is possible to encounter an undetected wind shear or microburst during the final approach or departure. Terminal Doppler weather radar is a relatively new technology that's being installed at airports to help improve the detection of both low-level wind shear and microbursts. Its narrow radar beam is capable of reflecting off minute particles in the air, such as dust and insects, and measuring the velocity of the air relative to the radar. Computers are used to calculate the wind speed loss or gain by comparing the air velocity moving toward the radar site with that moving away. The system can generate a microburst alert and 2 types of wind shear alerts. A microburst alert is issued for any headwind to tailwind speed loss of 30 knots or greater. For example,
microburst alert, 50 knot loss, 1 mile final.
The wind shear alert for a headwind to tailwind shear might sound like this.
Wind shear alert, 25 knot lost, 1 mile final, caution.
An alert will not be issued for a speed loss of less than 15 knots. A wind shear alert associated with a gust front or wind shift might sound like this.
Wind shear alert, 35 knot gain on the runway.
The Doppler system generates alerts for a specific runway. A 1, 2, and 3 mile corridor on final approach, and for 1 and 2 miles past the departure end of the runway. The alerts you receive are considered to be 90 to 100% accurate. Let's turn our attention now to some general operating considerations. Before any flight, and especially across country, check the weather reports and forecasts for potential wind shear and microburst activity. In addition, if you're on an instrument flight, be sure to maintain a stabilized approach so that any changes in aircraft performance can be easily detected. An unexplained change in airspeed, or rate of climb or descent, should be carefully evaluated for the presence of wind shear or microburst activity. At the first indication of wind shear or a microburst, apply maximum power and execute a go-around. This applies to VFR as well as IFR pilots. Some studies have indicated that the time available to recognize, react, and save the aircraft from an encounter with low-level wind shear is only 5 to 15 seconds, which is about the time it took to read this statement. The reason for this short reaction time is that the most hazardous events occur within 500 feet of the ground. In addition, the onset can be difficult to recognize. For example, during an ILS approach, a sudden increase in airspeed and pitch attitude may prompt you to reduce power and lower the nose to regain the glide slope. In a microburst, this could be a fatal reaction. About the time you intercept the glide slope, you enter the downdraft and the bottom falls out of the approach. You have a high sink rate, rapidly decaying airspeed, and reduced power. Even with an instantaneous application of full power, your airspeed continues to drop as you enter the tailwind portion of the microburst. Your only hope is to fly out of the microburst, if you have enough altitude. This is not a very pretty picture, especially in IFR weather. Be aware that low-level wind shear and microbursts can occur suddenly. They can develop between approaches while doing touch-and-goes. In addition, the aircraft ahead of you may not feel the effects of a microburst, while you may feel the full force. Anytime convective clouds are within 3 miles of the airport, you should be on the alert for low-level wind shear and microbursts. Even on a clear day, a fast-moving front can produce low-level wind shear. And remember, warm fronts may be more severe than cold fronts. In a general aviation aircraft, an encounter with a wind shear or microburst makes you a test pilot, since there are no set guidelines to follow. When flying in an area with potential wind shear, microbursts, or any weather hazard associated with a thunderstorm, it's important to concentrate on avoidance. If you're aware of the warning signs and remain alert for changes in aircraft performance, you may be able to avoid a potentially fatal encounter.